Now in R2, we know how to find the derivative of a function. Because in R2, a function is just a function of one variable. So this is the function y equals f of x, for instance, the function I have on here, f of x, y equals f of x. So if you want to find the derivative at the point A, this derivative is equivalent to finding the slope of the tangent line, the green tangent line, at the point x. Let's call it at the point A, sorry. And we know how to define this derivative. This derivative, we call it f prime of x at A. So f prime of A is a limit at h goes to infinity, or let's do f prime of x. Limit as h goes to, not infinity, 0. What is wrong with me? Of f of x plus h minus f of x all over h. All right. So, but if we want to find it at say A, then this would be A. A and A. All right. So that's the derivative of the function f of x at A. Now in R2, we don't have this. We have what we call partial derivatives. Okay. The partial derivatives are the derivatives in the x direction along the x-axis and the derivative along the y-axis. Now suppose we have a function whose graph is as follows. All right, so this is my z-axis, and that's the x-axis, and that's the y-axis. Now, we can decide to find the derivative of the function along the x-axis, or along the x-axis. So what does that mean? That means if, assuming we have a point here, this point, call this point AB, right? And we want to find the derivative of this function along the x-axis. Now, what that means is that we can take a cross-section of the graph, like a 2D cross-section of the graph, right? And then we can find the tangent line to the cross-section, the tangent line to the cross-section. That would be the tangent line, and then we can find the slope of this tangent line. All right, so remember here, this is the slope. F prime at A is just the slope of this green line. So slope here is f prime at A, right? So the slope here would be the partial derivatives. What we're going to define is the partial derivative with respect to x. All right, we haven't defined this partial derivative, but now we're ready to define it. The partial derivative, let's call it the partial derivative of f with respect to x at the point AB is its notation is f, this is the notation, at f sub x at AB, and this is the limit as h goes to 0 of f of A plus h then b minus f of AB all over h. Likewise, the partial derivative with respect to y at the same point will be f sub y of ab, and this is the limit as h goes to 0 of f of a, then b plus h minus f of ab all over h. But we're going to take another route of doing this. We know that these limits are limits involving functions of two variables. We're not going to worry too much about computing these limits. We're going to use a theorem, a developed theorem that I'm not going to state or anything. I'm just going to explain it for computing this derivative, okay? And I'm going to explain it with an example. Okay, so let's do an example. So I'm going to say find the partial derivatives You know what? Before I do this, I'm going to introduce other notations. All right. So we can have the notation fx, right, at AB or at xy. Let's do at xy. So this is the partial derivative of the function with respect to x. Or, and we can also have another derivative notation, df dx, right? And another notation is dx f f, right? For y, partial derivative with respect to y, then it will be fy or df dy or dyf, right? And then, so that means that something like never mind. I'm going to explain later on. I'm doing a lot of never minds in this video, but sometimes that happens. So now we're ready for an example. Let's find the partial derivatives. Find the partial derivatives. All right. So the first one, we have a function f of x. Or let's do this. F of x y is equal to 2x squared minus y squared, right, plus 7. Let's find fx of xy. Now, you have to listen very closely to what I'm about to say. Whenever you're finding the partial derivative with respect to x, you have to treat y like a constant. Treat it as a constant. And whenever you're taking the derivative, the partial derivative of f with respect to y, you treat x as a constant. So now, this one, we're looking for the derivative of f with respect to x. So we treat y as a constant. So we take the derivative of 2x. So fx, xy, the derivative of 2x is just 4x. Derivative of y squared, y is a constant, so it's 0. Minus 0, the derivative of 7 is 0, right? So we're done. This is just 4x. Now, b, let's find the partial derivative with respect to y. Okay. Now we're going to treat x as a constant. The derivative of 2x is now 0. The derivative of y squared is 2y, negative 2y. The derivative of 7 is 0. Now, I want you to find fx 1, 2 and fy 2, 0. So this just means take the partial derivatives and plug in the numbers you have in there. So fx 1, 2 is plug in 1 for x and plug in 2 for y. So if you plug in 1 for x, you have 4 times 1. We don't have any y in fx, so this is just going to be 4. And then fy 2, 0 is just going to be negative 2 times 0, which is 0. All right. Let's try another problem. Example 2. How about we find all the partial derivatives of, let's do g of x, y. G of x, y is cosine of xy. Okay. Now, let's find, how about this time, let's use the other notation, df dx. df dx is the same thing as just f sub x. df dx. Now, what do we do here? We have to remember chain rule. So you take the derivative of the outside and then you multiply by the derivative of the inside. But all your derivatives is with respect to x. So the derivative of cosine is negative sine. So we have minus sine of xy. And then we have to multiply it with the derivative of the inside. The derivative of xy, if you treat xy as a term, treat x as a variable and y as a constant, then the derivative of xy is just y, right? So it's just going to be y. So this is negative y sine of xy. Very good. How about, I would like you to try df dy. Try this. Okay. Now let's do another function. Let's do g of xy is equal to x squared e to the xy. All right. Let's do the first partial with respect to x. So I'm switching back to the other notation. I'm just moving around, doing notations up and down, doing different notations. So now, here we have a function times another function. We have x squared and then we have e to the xy. The product of two functions. So we have to remember product rule. So x squared times e to the xy. Product rule says the first times the derivative of the second plus the second times the derivative of the first. So we have the first, e squared times derivative of the second, e to the xy. Its derivative is e to the xy times the derivative of xy, which is just y if we're taking the derivative with respect to x, plus the derivative of e to the xy now times the derivative of 2x of x squared, which is just 2x, right? So you can, I don't know, well, x squared y e to the xy plus 2x e to the xy. Now, I'm going to ask you to try this. This is find the partial with respect to y. Try this one and tell me what you get in class. All right. Now, we're going to end by looking at what we call the second partial derivatives. All right? I'm just going to go ahead and do it. So, number 3, we have f of x, y is 3x squared y, 3x to the fourth y plus minus 2xy plus 5xy cubed. We're going to find all first and second order and second order partial derivatives. All right, so that means we're going to look for fx, or we're going to look for df dx, and then we're going to look for df dy, and then we're going to look for df dx of df dx, okay, and then we're going to look for df dy of df dx, okay, and then we're going to look for df, oh no, sorry, we're going to look for the partial derivative, the d dx of df dx, and then d dy of df dx, all right, and then we're going to look for d dx of df dy, and then we're going to look for df dy of df dy. Okay, so we're going to stop here, or maybe I should do one. So I'm going to do one. Let's take df dx, just find the derivative with respect to x. So this is going to give you 12 x cubed y minus 2y, right, plus 5y cubed. Okay, I'm sure you can do df dx, but now I want to do d dx df dx, right? So that means we are going to take the derivative of df dx with respect to x, okay? So this derivative that we have here, this, we're going to take its derivative again with respect to x. So we're going to have 36 x squared y minus 0 plus 0. All right, so what I want you to do, I want you to try this one yourself and then do the rest. Try this one and this and that, and we'll discuss it in class. My one final note is that I've been pronouncing this D and I've been writing delta, right? So that's just the way it goes. It's notation, it's delta. It's delta because we want to separate regular derivatives from partial derivatives, but we pronounce it D. All right. Okay. So we're gonna stop here. You'll notice something interesting between the first one, the third one and the fourth one. Yes. And what is that thing that's interesting? And next time we're going to talk about some alternate notation for this. Maybe I should do it now. So the notation for this one, instead of always writing these two deltas, we can do this. We can write this as d2f dx squared. Same thing here. We can write this as d2f d dy dx and so forth. This would be d2f dx dy, and this would be d2f dy squared. Okay. All right, we're going to stop here because I don't want this video to be too long. All right, see you in class or see you on the next video.